So now we will move on to Mohamed Mezouar, so from ESRF, and he will be telling us all about the revamped ID27. So please, Mohamed, go ahead.
Thank you, Dominique. And first, I'd like to thank also the organizers for the opportunity to tell you about the new opportunities that we'll have for high pressure science at the beamline ID27 on the newly built extremely brilliant source, EBS. Okay, so this is the outline. First, we'll give you just the basic principles of this EBS source, but Hans-Peter already touched this, so I will not go too far. Then I will say a few words about the scientific case that led to the construction of ID27, and give you the latest news about this instrument that will open very soon. Okay, so just a word about this basic principle of this new machine that is quite fantastic, I would say. It's based on a quite simple principle. If you look at the former ESRF storage ring, it was based on 2 magnetic elements here, and the EBS is based on 7 magnetic elements with a gradient of magnetic field along these elements. And you don't need to know about all the details of this. The result is quite fantastic because it leads to a reduction of the horizontal emitters, a tremendous reduction of the horizontal emittance, as you can see on this simulation made by Michael Wolf, a colleague at the ESRF. As you can see, you have a compression along a strong compression of the beam along the horizontal direction. Also, you gain a large fraction of coherent beam, as it was just said before by Hans-Peter. So this is the main characteristic of this new machine. So actually, before we decommission ID27, we could do some measurements on this instrument with the new source. And actually, we were very pleased, and we thought that the machine people did a really great job, because as you can see on this image, which is collected at about 40 meters from the source on a beam viewer, the source is a U35 undulator. You can see that the beam is about, it's almost a circle of 1 millimeter. Before the construction of EBS, we had a beam that at this position was about 26 millimeter. So you see that it led to a huge compression, but it's not all. As you can see on the next image here on this diagram, where you can see the undulator spectrum through a silicon 111 double crystal monochromator. You can see the undulator spectrum, and it's very nice. And as you can see here, when we focus on one of the harmonics, we have a highly symmetric and quite thin harmonic with an energy spread of about 0.5%, which is quite good, and it will allow us most probably to use this directly to perform, for example, X-ray diffraction experiments. Actually, if you compare to the situation with the former machine, and you see that the beam was highly dissymmetric, and you understand easily that it's extremely difficult to work with such a beam, not impossible, but very difficult to work with such a beam, because this symmetry translates immediately into the diffraction pattern, and it's very difficult then to deconvolute the different effects. And actually, we had also the time before we actually completely destroy ID27. We could still measure the focus beam at about 40 meters from the source, and we saw very clean, nice beam of the Gaussian shape. And actually, Hans-Peter insisted that it's nice to have small beam. It's more important to have a clean beam if you want to perform nice high pressure experiments. And we could get immediately a beam that was about 30% smaller than what we had before. And this is actually reaching the theoretical limits. And this opened great hopes about the performance that we could reach on the new beamline. Okay, but before going to specifically to ID27, I want to say a word about the high pressure activity in general at the ESRF on the new EBS storage ring. There is a large variety of X-ray techniques that are available there, like X-ray diffraction, of course, X-ray absorption spectroscopy, inelastic scattering, nuclear resonance scattering. And actually, you have also access to a diversity of sample environments, including the diamond anvil cell that you can combine with resistive heating or YAG or CO2 double-sided laser heating to perform very high or very high temperature experiments. You can combine also diamond cell with low T with helium cryostat to go at low temperature down to 4 Kelvin. We also have a nice large volume cell program, including a dedicated multi-anvil press, which is in monochromatic mode at ID6, and a parasite amber press that can go from beamline to beamline. And we just also started a nice dynamic compression program at 2 beamlines at ID25, where you can perform laser-driven experiments, shock compression experiments, and at ID19, where you can do X-ray imaging experiments in front of a gas pen facility. And with all these techniques, you get access to the electronic, magnetic, structural modification that occur under extreme PT conditions. So now I will tell you more specifically about the upgrade of ID27. And the general context of building this instrument was because it was actually an instrument that was running for almost 15 years, and it was time for change. So we proposed a new instrument, and we actually followed the opportunity of the EBS to build actually a beamline that is optimized for the source, and we called it iFlux Nano diffraction beamline for study for science under extreme conditions. So actually, to defend this project, we defined 4 key scientific areas. And the first one was actually discussed by Hans-Peter, is to study materials at and beyond the current limits of static pressures and high temperatures. And for this, you need, of course, very high spatial resolution, down to 300 nanometers. Another domain that was important, we found important, was the possibility to study the structure and chemistry of low Z melts and glasses at extreme conditions. And for this, you need quite high flux, and the necessity to use probably the ping beam work in ping beam mode. Also, the possibility to study fast melting, kinetics of chemical reaction, and in this case, you have to enter the time domain down to the microsecond. And finally, to exploit the high coherence of the new machine, to the possibility to do rheology of materials by using fast X-ray imaging. So I selected a few examples for that. The first one I will not discuss because it was discussed at length by Hans-Peter. I can give you another example. For example, if you look at the phase diagram of hydrogen, it's a very classical problem in high pressure physics, and geophysics, of course, because, for example, hydrogen is one of the main components of Jupiter. Looking at for example, the dissociation, the transformation from molecular hydrogen to atomic hydrogen that is predicted by several calculations, looking at that experimentally is a tremendous challenge, and is not possible to perform at any source, synchronous source today, because for this you need a very high flux, photon flux, and this can be provided by only if you move to ping beam operation. Okay, another domain where the new EBS could play a key role is looking at fast melting, kinetics of chemical reaction under extreme condition, and looking at processes that occur at the center of below our feet in the depths of the earth, in the mantle, and also in the core, and looking at the interactions. And for this, we have to convert the beamline into a nano beamline, where it's possible to combine diffraction and fluorescence. The fluorescence will be essential to look, for example, at the element distribution in the diamond anvil cell. Even at moderate pressure, when you do laser heating, you know that sample are inhomogeneous, and you will need a very small beam to map the elements in the diamond cell. Look at exactly what happened in the diamond anvil cells, and for this you need a much smaller beam. Okay, this is all for the examples. Now I will say a few words about the beamline itself. So the main objective was here to build a new diffraction beamline that can combine diffraction with fluorescence and imaging. and take the full advantage of the EBS. And the basic principle on which this beamline was based is that we wanted to reduce the number of optical elements to a minimum in order to improve the stability of the beamline and optimally exploit the intrinsic beam properties of the EBS. Of course, we had to exploit the very low horizontal emittance, and which is a big advantage because then you have no need for a secondary source, and it leads to a very simplified optical configuration in the horizontal geometry, which is more stable than the vertical geometry. And the main, I don't want to enter into the detail, just the main elements of this beamline are a DMM, which is a double multi-layer mirror that provides a pink beam. And then we have a DCM that we can put in and out. So we could work in monochromatic and pink beam mode just by translating the DCM along the beam. And our choice for focusing and to obtain very clean beam is, by experience, is that my point of view, of course, there's many other possible choice, but I prefer, my personal choice is to use KB mirrors. So we decided to implement 3 KB mirrors in front of the experimental table, and then also a big detector holder. So what are the main features of this beamline? So we want to have a high flux beamline. So for that we choose the U18 undulator, which was the optimum for us in terms of flux and tunability. So we expect a gain in flux typically of 100 in monochromatic mode at about 30 kV, and a factor 1000 in peak beam. So it's really a tremendous gain in flux for this beamline. Also, this beamline will be converted into a long beamline of 120 meter long, and this is essential for producing the nano beam without compromise on the diffraction side, because you can still put the mirrors at a certain distance from the sample and allow for nice sample environments. It's also important for full field X-ray imaging. We will also want a tunable energy from 15 to 60 kV, where this will allow combined diffraction, fluorescence, and X-ray imaging again. And we want also a lot of degree of flexibility. So for this, we implemented switchable optics for a monochromatic operation for high resolution nano and micro diffraction, and high energy coherent X-ray diffraction and imaging. For pink beam operation, for time resolved X-ray diffraction, X-ray fluorescence, and imaging, and also for time resolved experiments down to 1 microsecond time scale. And also, we wanted a variable focal spot from 250 nanometer by 200 nanometer up to 10 by 10 microns to cover a very large number of applications, not only for the extreme, but also, we want to cover everything. And for the X-ray detectors, we opted for a large area, high energy filament telluride pixel detector, which is state-of-the-art detector nowadays. It's you can reach this kind of rate, 250 hertz frame rate, which is compatible with the flux that the flux enhancement that we will have. So where are we today? So this is the first optics hatch, the white beam optical hatch. Actually, the status of this hatch is that it's finished, and we already a month ago we installed the double multi-layer mirror, which is a water-cooled system. It was an in-house development, which shows actually all the expertise that we have at the ESRF to produce state-of-the-art optical elements. And actually here you can see a photo that I took actually my colleague Wolfgang Morgenroth took this morning on this hatch. Then on the second hatch, where the monochromator is installed, we already quite advanced. Actually, the double crystal monochromator, which is a silicon 111, because we want to have about 10 to the minus 4 energy resolution, is fully tested at the ESRF metrology lab, and it will be actually installed tomorrow morning at the beamline. And this was actually a development of the German company Epsilon, following our specifications. Okay, now a word about the end station. As you can see on this image, this is a quite large hutch, which is thermostabilized at plus or minus 0.1 Kelvin. In order, because for the nano beam, this puts a lot of constraint on the thermal and vibrational stability in the hutch. It is composed of 5 very heavy granite assemblies, one for the KB mirrors, the 3 KB mirrors that are here. Then we have 3 goniometers, one laser for the laser heating, 1 nano station for nano mapping of samples, and one for called heavy duty, where we do all the rest like cryostat, parasilamber cell, and so on. We have a granite also for ancillary equipment, including the Raman and PRL and solar states and other systems, and also will be some free space for improvised setups. Okay, so we want to leave also to the users the possibility to do their own things. Then we have a granite assembly for the detectors, and final granite assembly for 2 CO2 lasers, because we also want to perform a double-sided CO2 laser system. So it's quite a lot. And this is a photograph that actually Wolfgang took this morning on the hutch, so we're quite advanced. So you can see that one of the KB systems already in place, all the granite assemblies are in place, and the detector systems, the detector mechanics also there. And I will not say a word about this because I'm out of time. And okay, this is a summary of the performance that are expected. Just one word about the deadline for next beam time application. So this beamline will be ready is open to users. Since the previous round actually was partially open, now it's fully opened. 100% of the beam time will be available for the next round, and you can apply for it. The deadline is luckily it's in 2 weeks. So thank you for organizing this meeting in a very timely fashion, so that people have time to put proposals. And with this, we'll begin with the acknowledgement and the people that helped with the project. And thank you for your attention.
Thank you very much, Mohamed. So this sounds again very exciting. Now I just need to find a way to get beam time, and then we'll be perfect. So I don't
not
see
so difficult.
Not so difficult.
Well, you had a lot of beam time in the past, so just have to write good projects.
So I don't see any hands raised, so I'll just take the time to ask one very short question. I was wondering what would be the confusion sphere of the rotation motor underneath the deck.
So yeah, if you look here, there is actually in the center here, we'll have a nano station. So all the goniometers will have different sphere confusion. The best one, which will be really adapted to the nano beam, is a nano station, and in this one the sphere of confusion will be something like 300 nanometer for 180 degrees. So it's still under test at our metrology lab, but the factory test confirmed that they had about this performance.
Very good. Thank you, Mohamed.